of u के जितने भी नेबर है that belong to the path P. Now since u has at least k neighbors, because k इसका डिग्री है k, at least k, u has at least k neighbors, and since g is simple, so P therefore has at least k vertices other than u and has length at least k. So what it tells, since जैसे यहाँ पे अगर मैं देखूं तो every vertex has at least 3 neighbors. Okay, so we should say that, so what it tells in this figure, every neighbor has, sorry, every vertex has at least degree 3. Then G contains a path of length at least 3. Why that is so? Since 3 के जितने भी neighbors हैं that will be on the path, so एक neighbor 2 that is on the path, second neighbor 4 that is on the path, एक neighbor 5 on the path. So at least 3 2 4 5 ऐसा एक पाथ आ ही जाएगा. मतलब एटलीस्ट 3 लेंथ का पाथ तो मिलेगा ही. यहाँ पे तो उससे ज्यादा मिल रहा है, 3 2 1 4 5 4 लेंथ का पाथ मिल रहा है, पर मुझे 5, जैसे इफ यू लुक इनटू 5, it has at least 3 neighbors, still 4 neighbors, so 4 is a neighbor, 1 is a neighbor, 2 is a neighbor, 3 is a neighbor. So if it has 4 neighbors, you see that there is it always gives rise to a path of length 4, because first neighbor यहाँ पे रहेगा, दूसरा neighbor के बीच में, मतलब there cannot be parallel since it is a simple graph. So second neighbor must be different from 4, third neighbor must be different from this 1 and 4, and fourth member different from 4 1 and 2. So this, for this 4 so if it has degree at least k, then it has k neighbors, and all this, since all the neighbor is on the path, so the length of the path is k. And it says that if k greater than equal to 2, then G also contains a cycle of length at least k plus 1. This is also very simple to see, because since 3 is the neighbor, so this path of length k plus this edge will give a length of k plus 1. Okay, so basically it tells that then the edge u to its farthest neighbor. So you have a path P, along with that, if you, with this path, if you add the edge from u to its farthest neighbor v, then it will give you a sufficient long cycle of length at least k plus 1. Okay. Next theorem is every graph with a non-loop edge.
Sir, can you explain that cycle part again?
Cycle part? Yeah, so basically, say for example, in this graph, we have 3 neighbors. So we have, so first neighbor is here, second neighbor is here, third neighbor is neighbor. So it has a path of length 3. It will always have at least 3. उससे ज़्यादा भी हो सकता है, यहाँ पे जैसे उससे ज़्यादा है. Now it says that it has a cycle of length k plus 1. That means ये जो path है, along with the तो 3 का farthest neighbor कौन है path में? Farthest neighbor with respect to the path. 3 का नियरेस्ट नेबर है 2, सेकंड नियरेस्ट नेबर है 1, थर्ड नियरेस्ट, सॉरी फर्स्ट नियरेस्ट, सॉरी 3 का नियरेस्ट नेबर है 2, सेकंड नियरेस्ट नेबर है 4, फार्थेस्ट नेबर है 5. फार्थेस्ट मींस with respect to the path, with respect to the maximal path. It is farthest neighbor means with respect to the maximum path. So farthest neighbor v along path P. So ये path का length k होगा, along with that 3 का farthest neighbor है 5, तो इसको मैं अगर ऐड करूंगा तो this will give rise to a cycle of length k plus 1. जैसे 5 का भी farthest neighbor है 3, तो इसको अगर मैं ऐड कर दूं, this is the path of length k, along with that this edge is added, it will give rise to a cycle of length k plus 1.
Okay, sir.
So every graph with a non-loop edge has at least 2 vertices that are not cut vertices. So कोई भी ग्राफ में, बेसिकली अगर कोई सिंपल ग्राफ ले लो, उसमें एटलीस्ट 2 वर्टेक्स तुमको मिलेगा which are not cut vertices. Again, it's very easy to prove. So since it is a graph, you have a maximal path P, and it has two endpoints U and V, and you know that the neighbors of U will always lie on P. As a result, since neighbors of U lie on P, if you delete U, then P minus U is also connected in G minus U. So the neighbors of U belong to a single component of G minus U. So U cannot be a card vertex. And this is also true for the other endpoint V of the maximal path P in G. So it's very straightforward proof. If you follow the last, जैसे इसको देखो. So take this graph. This is the maximal path U214V. Now if I delete U, then in this G minus U214V, everything is in the path itself. So everything is in the graph itself. They cannot be disconnected. Why? Because since it is the maximal path, U के जितने भी neighbors हैं, that must belong to this path. To U के एक neighbor है 2, एक है 4, एक है V. So if I delete U, these edges will be deleted, but since 2, 4V, they belong to this path. So there is always, they must be connected. So U cannot be a card vertex. In a similar line, V cannot be a card vertex. Because if I delete V, so we can take another picture. Suppose if I delete V, what happened? So if I delete V, then also it is connected. And so if U is given the graph G, we have a maximal path P, and you know that every neighbor of U must lie on the path. So automatically they are connected through this path. That is why if I delete U from the path, so all other vertices, that is neighbors of U, they are also connected in G minus U through this path. That is why U cannot be a card vertex. And the same reason can be given to the other extreme end of the maximal path, that is for the vertex V. So now there is a definition of decomposition of a graph. So decomposition of a graph means partitioning the graph into subgraphs such that each edge appears in exactly one subgraph. Okay, so the vertex can be repeated. So for this graph, these are two decompositions. So UV24 and V412. So these are decompositions. So partitioning the graph into subgraphs. So यहाँ पे देखो 24V. These vertices are repeated in both the subgraphs, but edges appear in only once. U2 appears here, so it cannot appear here. U4 appears here, so it doesn't appear here. So that is how. So partitioning the graph into subgraphs such that each edge appears in exactly one subgraph. It must appear. So if I decompose it, the edge must appear in one and only one subgraph. Okay. The vertex may be repeated, but it need to be repeated. Otherwise, how can we decompose? This is a definition. So
basically, sum करने से original graph वापस मिल जाएगा.
सम बोल सकते हो इसको, इस फंक्शन को हम सम कैसे बोल, हाँ मतलब if you merge
overlap
these two, if you merge these two, you will get back the original graph. Yes, but with the constant that edge appears exactly once. जैसे 2,4 can't be appeared here. Okay, because if you merge them, then it will give you parallel edges. so edges repeated exactly once. Now this is a very important theorem and it's a nice observation also. So basically till now we are dealing with I should say, so basically we are dealing with Euler graph. So what is Euler graph? Euler graph में हर एक vertex का degree even है. Now so if all vertex has even degree and if the graph is connected, we know that we can find a closed trail, which is called Euler trail. Now it may so happen in some graph, we have already proven it, that every graph has even number of odd vertices. Okay, so for a general graph, if it has 2k odd vertices, so it is a general graph. So it is a connected non-trivial graph. That means the graph has at least one edge. It is a connected graph, so there is a single component with exactly 2k odd vertices. Then the minimum number of trails that decompose it is maximum of k comma 1. Okay, so the minimum number of trails that decompose this graph is equal to the maximum value of k and 1. So how do you prove it? So first एक simple चीज proof कर लेते हैं. Suppose you are given a connected non-trivial graph where there is no odd vertex. So every vertex is even. That means that is an Euler graph. So k का value is 0. So in that case, the minimum number of trails needed is 1. Why? Because that trail is nothing but the Euler trail itself. So for one part we need to prove it, and this is true only for Euler graph. So if the connected non-trivial graph has 0 odd vertices, in that case the minimum number of trails needed to decompose it is maximum of k, that is 0 comma 1, that is 1. And why this 1 came? Because at least one trail तो लगेगा ही आपको एक Euler trail को trace करने के लिए. Okay. Now if k is not equal to 0, that is k has either value 1, 2, 3 or 4 and so on, it at least has even number of odd vertices, then the minimum number of trails needed to decompose it is actually k. So अगर 2k odd vertices हैं where k is not equal to 0, in that case minimum number of trails needed to decompose it is basically k. Now मैं proof में नहीं जा रहा हूँ, proof आप लोग एक बार read कर लेना. तो कैसे basically the outline of the proof is, अगर ऐसा एक ग्राफ मुझे दिया जाए, given a graph which has 2k odd vertices, how can I decompose it into k trails? Okay, so that is the basic question. अगर mathematically मैं इसको सोचूं, you are given a connected graph, non-trivial graph of 2k vertices, then what is the procedure or what is the algorithm to decompose the graph into k different trails? Okay, so basically the algorithm goes like this. Okay, so basically what happens, you look into this graph. This graph has 4 odd vertices. So this is even vertex, this is odd vertex, 4 is also odd vertex, 5, 3. So there are 4 odd vertices. So basically 2 into 2 odd vertices. So k ka value is 2 for this graph. Now the question is, how can I decompose this graph into 2 trails? That is the basic question. If we look here, for a connected non-trivial graph of 2 into 2 odd vertices, the minimum number of trails needed to decompose it is basically k. How do we do this? Basically what we do, we pair up any 2 odd vertices. So यहाँ पे मैं क्या किया, 3, 5 को मैं एक pseudo edge से connect कर दिया and 2, 4 को एक pseudo edge से मैं connect कर दिया. Why do I do this? It will create a even graph. Now every vertex has even degree. 3 has degree 4, 5 has degree 4, 2 has degree 4, 4 has also degree 4. Now this graph, since it is an even graph and it is a single component, then we can easily construct a Euler tool for this. So what we do for that, the algorithm is as follows. We create a Euler tool for this. So suppose I start from 3. I go from 3 to 2, I go. And okay, so basically for this, कैसे हम लोग Euler tool create करेंगे? तो we divide it into few cycles. 3, 2, 1 for एक cycle है, 2, 4, 5 एक cycle है, and 3, 5 एक cycle है. Suppose I start my journey from 3. I go from 3 to 2. So basically I am trying to explain here कैसे मैं इस tool को कर रहा हूँ. So मैं यहाँ पे 4, 5 से चलूँ. मैं इस एग्जाम्पल को, suppose I start from 4. From 4 I go to 5. At 5 I see that, so 4 to 5 I go by the blue cycle. Here I see there is a detour is possible, so I go to 3. From 3 okay. Suppose I go from 4 to 5. 4 to 5. From 5, I can continue with the blue cycle or I can go to the red cycle. So I will always go to the red cycle. Okay. So from 4, 5, I will go to first 3. So once I reach 3, I see that there is a new green cycle. So I continue along this green cycle. 3 to 2, 2 to 1, 1 to 4, 4 to 3, then 3 to 5, then 5 to 2, then 2 to 4. Okay. So I get a Euler tool here. Now among this, when I create this tool, I know that these two edges are used, 5, 3 and 2, 4. Okay. So at that juncture, I need to break it. So I first go to 4, 5, then I go by 5, 3. So 5, 3, ये tool actually नहीं है original graph. So I will break it. Then I go by from 3 to 2, 2 to 1, 1 to 4, 4 to 3, 3 to 5, 5, sorry, any problem? 4, 5, 3, 2, 1, 4, 3, then 5, then 5 to 2, sorry, 5 to 2 and 2 to 4. Again, this 2, 4 is not important. Okay. So basically I get two non-closed trails. The first trail is 4, 5 and the second trail starts from 3 and ends at 2. Okay, ends at 2. So 4, 5 is 1, 2 and the second tour is 3, 2, 1, 4, like 3, 2, 1, 4, 3, 5, 2. Okay, so these are the two trails I have got. So basically what this algorithm says, that if you are given any graph having 2k odd vertices, how can I divide it into k different trails? Okay. So इसका प्रूफ है, फॉर्मली यहाँ पे प्रूफ है, प्रूफ रीड करोगे समझ में आएगा, इतना डिफिकल्ट नहीं है. बट बेसिकली इसमें चैलेंज है जो एल्गोरिदम है वो कैसे हम एग्जीक्यूट करेंगे. एल्गोरिदम के लिए यहाँ पे वो एल्गोरिदम लिखा गया है पूरा. तो बेसिकली ये एल्गोरिदम को ऐसे डिपिक्ट किया गया है कि you first from that graph you create a Euler graph, then you take a Euler tour for that. Now once when you pass through this dotted edge, you think that a new tour should be started. So 4 to 5 normal graph, then 5 to 3 it is a dotted edge, so a new tour start from 3. So 5 3 actually doesn't exist. From 3 I go to 3 to 2, 2 to 1, 1 to 4, 4 to 3, 3 to 5, 5 to 2, and come back to 4. Now this 2 4 again doesn't exist in actual graph. So there are two tours. One is 4 5. This is given by this. Another is 3 2 1 4 3 5 2. So 3 2 1 4 3 5 2. So these are two non-closed tours. So 4 5 they are two different vertices. So that is a non-closed trail. Again यहाँ पे भी जो tour है that starts at 3 ends at 2. But this is a closed trail. Sorry, it is a non-closed trail which visit all the edges exactly once. Okay, so that is how I create two different trails. Now we move to a new topic, that is called isomorphism. Okay. So the next topic is isomorphism. So what is isomorphism? It is basically nothing but a bijection. So when I talk a graph, there are given two graphs. This is graph G, this is graph H, and we say that. So what are the conditions? We say that G is isomorphic to H. So a simple graph G is isomorphic to a simple graph H is nothing but a bijection from the vertices of G to the vertices of H, such that if UV belongs to EG, UV belongs to the edges of graph G, if and only if, since F is a bijection, so FUFB belongs to EH. जैसे ये दो ग्राफ में A is mapped to W, B is mapped to X, C is mapped to Y, and D is mapped to Z. Okay. So this is the bijection. So if given two graphs, if somebody asks you to prove that they are isomorphic to each other, then your task is to give this bijection. So it is true for simple graph. Okay, so it is, this definition is basically isomorphism in simple graph. And how it is different from non-simple graph? Because non-simple graph has multiple. Now in non-simple graph, it may so happen that between two vertices there are multiple edges. Okay, or there might be self loop also. So for non-simple graph, the definition is a bit different. But for simple graph, it is basically you have to match, if given two vertices G and H, your task is to create a bijection across the vertices of two graph G and H, such that if UV belongs to EG, if and only if FUFB belongs to EH. Okay. And this isomorphism symbol is G triple equal to this basically equivalent symbol, G equivalent H, if there is an isomorphism from G to H. Now isomorphism for non-simple graphs is like this. यहाँ पे सिर्फ vertex mapping is not important. You have to do this bijection on not only on the vertices but also on the edges. So both vertices and edges, for both of them you should create a bijection. If the bijection exists, then you can say that G, a non-simple graph G, is isomorphic to a non-simple graph H. Say for example here, again here Fa equal to W, Fb equal to X, Fc equal to Y, and Fd equal to Z. Now between A and B we have two edges E1 and E2. तो यहाँ पे ए बी के बीच में E1 E2 है, दैट मीन्स WX के बीच में दो एज रहना चाहिए. सो WX के बीच में दो पैरेलल एज है, one is H1 and another is H2. So we have to write that this E1 map to H1 and E2 map to H2. So that bijection is also need to be mentioned. So along with this we have to mention that f of E1 equal to H1 and f of E2 to H2. सिंपल ग्राफ में आइसोमॉर्फिज्म में सिर्फ वर्टेक्स मैपिंग इज इंपॉर्टेंट टू शो. इन नॉन सिंपल ग्राफ वर्टेक्स मैपिंग as well as edge mapping, or I should not edge mapping, edge bijection should be shown. Self complementary graph, if a graph is if a graph is isomorphic to its complement, then it is called a self complementary graph. So जैसे A B C D, इसका कॉम्प्लीमेंट ग्राफ कौन सा होगा? यू टेक द सेम वर्टिसेस बट यू डोंट टेक द एजेस. तो यहाँ पे ए बी एग्जिस्ट कर रहा है, तो दिस ग्राफ में ए बी कैनॉट एग्जिस्ट. यहाँ पे ए सी डजंट एग्जिस्ट, तो यहाँ पे ए सी मस्ट एग्जिस्ट. बी डी डजंट एग्जिस्ट, तो बी डी मस्ट एग्जिस्ट. ए डी डजंट एग्जिस्ट हियर, सो ए डी मस्ट एग्जिस्ट. Okay, now you see that this graph is complement to this and they are isomorphic to each other. So here A is isomorphic to B, this B is isomorphic to D, this C is isomorphic to A, and this D is isomorphic to C. Okay. So okay, now this is called automorphism. So automorphism is basically isomorphism from G to G itself. जैसे A B C D. Okay, now this graph is isomorphic to the graph G itself in the terms DCBA. So A B C D and this is DCBA. So now A is isomorphic to D, B is isomorphic to C, here C is isomorphic to B, D is isomorphic to A. So this is called an automorphism. So a graph is isomorphic to itself. So any graph is isomorphic to itself. That is true. But here it says that automorphism किसको बोलेंगे? An isomorphism from G to G, जहाँ पे you can, so given a vertex A in graph G, you can biject this vertex to some other vertex other than A. So they say A is mapped to D, B is mapped to C. So अगर मैं ये कर देता कि A is mapped to A, B is mapped to B, C is mapped to C, so for all graph this automorphism, so definitely for all graph there is a single automorphism at least, but in some cases there can be more than one for this kind of graph where A can be mapped to D, B can be mapped to C, C can be mapped to B, and D can be mapped to A. A graph G is called vertex transitive if for every pair UV belongs to VG, there is an automorphism that maps U to V. इसका मतलब ये है कि कोई भी vertex, so suppose you took this graph, you take any one vertex, and if you create a bijection with B with all other vertices, like B can be uh, assigned as A, B can be assigned as C, B can be assigned as D. If that is the case, that is called as vertex transitive graph. So I will again repeat this. When a graph is called vertex transitive, if for every pair UV belongs to VG, U can be mapped to V. जैसे ये तो ग्राफ ऑटोमॉर्फिक है, but they are not vertex transitive. क्यों? क्योंकि A cannot be mapped to C. Yeah, B cannot be mapped to D. That is not possible. So this cannot be vertex transitive. But C4, like if you take a graph like this, okay, so suppose it has few vertices. Now, if I give them some name, suppose this is A, this is B, this is C, and this is D. Now you see that A can be mapped to any one other vertex. A can be mapped to B also. If I map A to B, then B should be mapped to C, C should be mapped to D, D should be mapped to A. Okay. Or it may be the other way around. If you can map A with B, then so A if mapped to B, then B mapped to C. Yeah. Again, A can be mapped to C also. If A is mapped to C, in that case B will map to D, C will map to A, and D will map to B. Okay. So every pair of vertex can be mapped to each other in two different graphs. So that is called vertex transitive. So C4 is a vertex transitive graph. It is not only C4, any CN is a vertex transitive graph. Okay. Yes. Now, a new kind of graph is called hypercube. So hypercube, how do we define or how do we create hypercube? So a k-dimensional hypercube, a k-dimensional cube or hypercube QK is the simple graph whose vertices are k tuples with entries zeros and ones, and whose edges are pairs of k tuples that differ in exactly one position. Okay. So basically, the objective is, so if it is a k-dimensional hypercube, it should be the notation used for hypercube of order k is qk. Okay. Now it has 2 to the k vertices. So suppose it is Q3. So it has 2 cube, that is 8 vertices. Each vertex is basically the binary numbers. So 0, 0, 0 through 1, 1, 1. Okay. Now how the edges are being created? Like 0, 0, 0 and 1, 0, 0, there is an edge between them because these two bit pattern are differ by exactly one position. So this 0, if I convert it to 1, it gives me this vertex. Similarly, if I can convert the middle one to be 1, so 0, 1, 0 is another connecting vertex, so 0, 1, 0, and 0, 0, 1 is the third one. You take any one now, suppose 0, 1, 1. So you flip 1 to 0, so 0, 1, 0, you get this vertex. Suppose you take if you flip the middle one to 0, so it becomes 0, 0, 1. So this is that vertex. And the third vertex is 1 1 1. So if we flip this 0 to 1, then 1 1 1. So 1 1 1 is the third vertex. So that is how you create this hypercube. Okay. So then a j-dimensional subcube of Qk is a subgraph Qk isomorphic to Qj. Okay, we will look into this. So what is Q0? Q0 has a single vertex 0. What is, because it has 2 to the power 0 vertex. 2 to the power 0 is only one vertex, so it has 0. Then you have Q1, it has two vertex 0 and 1, and there will be a single edge because 0 is flipped to 1. Now you have to create Q2. How do you create Q2? So you take 2Q1. You take 2Q1 like this. Okay, this is one Q1. This is the next Q1. So यहाँ पे this is 0 1. So if you took into the LS bit, least significant bit, so this is 0 1. This is also 0 1. Then what we will do to create Q2, इसके पीछे प्रीपेंड कर दो 0. Q1 के, ये Q1 के कॉपी लो, यहाँ पे Q1 के कॉपी लो, इसके साथ 0 प्रीपेंड कर दो, इसके साथ 1 प्रीपेंड कर दो. So 0 0 0 1 and 1 0 1 and you connect them. Okay. From Q2, how you create Q3? So basically what you do, you take two copies of Q2. So this is one copy of Q2. This is another copy of Q2. Now what you do, ये Q2 कॉपी में पिछले सब 0 लगा दो. यहाँ पे 0, यहाँ पे भी 0. This also has 0 and this also has 0. और इसके पीछे 1 लगा दो. नाउ ये 0 0 के जो कोरेस्पॉन्डिंग वर्टिस है उसको ऐड कर दो. यहाँ पे भी 0 0 है, यहाँ पे भी 0 0 है, तो इसको ऐड कर दो. ये 0 1 था, यहाँ पे राइट हैंड में 0 1 है, तो यू ऐड देम. यहाँ पे 1 1 था, यहाँ पे भी 1 1 है, you add them, and finally we add this, the right two bits is 1 0, यहाँ पे भी 1 0 है, so we'll again add them. So this will give you Q3. Okay, so this will give you Q3. तो यहाँ पे भी So this is one copy of Q2 and this is another copy of Q2. And you merge them like this. So prepend 0 in one component, prepend 1 in one component, and then corresponding vertices are added. So you get Q3. Now, some theorems. If it is a k regular bipartite graph, if k greater than 0, then a k regular bipartite graph has the same number of vertices in each partite set. Okay. So, though it's very trivial to prove, but anyways, if let G is an xy bipartite graph having degree v equal to k for all v. Okay, so that is the thing that is given. Suppose it is the xy bipartite graph. Each vertex v in each partite has degree k. Now counting, if we count the edges according to the endpoint of x, so then what is the number of edges? Eg equal to k into mod x. So mod x is the number of vertices in partite x, and each vertex has k degree, so k into mod x is total number of edges. Similarly, counting the edges by the endpoints in partite y also give Eg equal to k into y. So partite y has y number of vertices, mod y number of vertices. Each vertex has degree k. So number of edges k into mod y. Now since this is both graph is the same graph, so k into mod x equal to k into mod y. So k cancels out. So mod x equal to mod y. It means that both partites has equal number of vertices. So same number of vertices are there in each partite. So these are more straightforward. The minimum number of edges in a connected graph with n vertices is n minus 1. That we already know. And this happens in a tree. Okay, so we know that this happens. This kind of connected graph is nothing but a tree. Similarly, every graph with n vertices and k edges has at least n minus k components. Okay, so these two things are actually known facts. You can you can prove it also, but this proof is very simple. So if you want to try it out, you try it out at your own. Okay. Now the theorem says if G is a simple graph, and it is an n vertex graph, where each vertex, where the minimum degree is greater than equal to n minus 1 by 2, then the graph is connected. So what it tells, okay, you are given a n vertex graph. Every vertex in this graph has at least degree n minus 1 by 2. Delta G basically says that the degree of so delta G denotes the degree of the so it basically gives the minimum degree of the graph. So every vertex has at least this much degree delta G, which is given is at least n minus 1 by 2. Then you have to prove that this graph is connected. So if you want to prove some graph is connected, what we are supposed to prove, that given any two vertices u and v in the graph, there is a path between them, right? So that is something you have to prove. So choose u and v belongs to Vg. So you choose any two vertices in this graph. If you see, there are two cases possible. If u is adjacent to v, so u is connected to v. So done. Now suppose u is not adjacent to v. Then we have to prove that. Then we will prove that u and v both have a common neighbor. So that common neighbor, if that is called k, then ukv gives me the path, and which says that uv again connected. So that is something we need to prove. So what is given here? You are given the n vertex graph. You say that every vertex has a degree n greater than equal to n minus 1 by 2, and you are supposed to prove that it is a connected graph. So by connected, we mean that given two vertices in the graph, they are connected by a path, at least one path. So we choose any arbitrary two vertices u and v from the graph, and u is adjacent to v. Case 1. In that case, we know that u and v are added by an edge, so they are connected. So done. If u is not adjacent to v, then we have to prove that they are connected, and we prove here is that for this kind of graph, u v have a common neighbor. How do we prove it? So nu denotes the neighbor of u. So the vertices we are neighbor of u. So neighbor u intersection neighbor of v. So from set theory we know that it is nu plus nv minus nu union nv. Okay. Now what is the number of vertices eu? So how many neighbors are there for you? It is greater than equal to n minus 1 by 2, and this is same true for nv also. So mod nu or mod nv, whatever it might be, since delta g greater than equal to n minus 1 by 2, so nu comma nv must be greater than n minus 1 by 2. Now what is nu union nv? If I take nu and union nv and u is not adjacent to v, that means it must be less than equal to n minus 2. Why this is true? So neighbor of u union neighbor of v. So u के neighbor v नहीं है, again v के neighbor u नहीं है. So neighbor of u के सेट में v नहीं रहेगा, v के सेट में u नहीं रहेगा. So मैक्सिमम कितना neighbor हो सकता है? ये टोटल सेट में u भी नहीं है, v भी नहीं होगा. So uv अगर मैं निकाल देता हूं तो मैक्सिमम नेबर हो सकता है n minus 2 नेबर. So nu union nv is less than n minus 2. So minus nu minus nv is greater than equal to minus n minus 2. It's simple mathematics. Now you see that what is nu intersection nv? It is nu plus nv minus nu union nv. So this is given as greater than equal to n minus 1 by 2. Nv is also greater than equal to n minus 1 by 2. And minus nu union nv is greater than equal to minus n minus 2. So this gives 1. That means nu intersection nv, neighbor of u intersection neighbor of v, has at least one vertex. So uv has a common neighbor. So that is how we prove that. That is how we prove that if you are given an n vertex simple graph where every vertex has degree n minus 1 by 2, then the graph must be connected. So with this I end today's lecture, and that's all. So next Friday 10 to 12 we have a class, so we'll meet there. Thank you.
Thank you, sir.
Thank you, sir.